So welcome everyone, and thanks for your interest in our work. I will now present you this work that we did with an undergraduate student, Juliette Ortholand, and a colleague, Khaled, Belahcene, and myself, Sébastien. So this work is about equity in learning problem and using OWA, or ordered weighted averaging, approaches to do so. So the research question we address is that when learning a model, can we increase accuracy with respect to a minority without giving up too much of average accuracy? So in this work, we work within a given hypothesis class, which means that we will not use ensemble methods or iterative methods such as bootstrap. And our goal is to adapt the loss function to our problem. And why such choices, would you say? One thing is that this way, the model does not get more complex. So if we have interpretability, we keep it. We want basically to be model or method agnostic to ensure better minority treatment. And also, the model we trained and validated may have been done painfully so, especially if we deal with XAI or interpretable models. Okay, so here you have an illustration of the problem we want to tackle. So here you have two populations, two classes, blue and red, and two populations. So you have a clear minority on the upper right, and population which is the majority, let's say, which is in the middle. So what you see is that if you train a model with weighted averaging, the majority is more or less well treated. The blue are well separated from the red. But if you look at the minority, then this minority is very poorly treated by the models, and you make almost systematic error on the blue, on the red population, right? In this part here. So okay, so what's the idea? The idea is that when you train a model, you try to minimize the empirical risk, which is here. It's just the arithmetic mean of the loss function between your prediction, hxi and yi. So the idea is that sometimes this empirical risk may have some problems. So the first thing is that it may poorly reflect reality when basically you violate the ID or identically and independently distributed assumption on the data. For example, in non-stationary systems. Another thing that ER might actually do poorly is that it may poorly reflect our values. So empirical risk assumes risk neutrality. So the question is that, are we risk neutral? And it also corresponds to a very utilitarian view of social welfare. So are we in the case where we want to protect minorities? But still, empirical risk is very nice, especially if the loss function is convex, because it has an additive form, and also so we would like to keep the additive form, but weight the data set non-uniform. So the idea in our proposal is to keep what is good about the empirical risk and try to remedy to what is bad for it. So the idea is that, as I've said, we adapt to the principle of loss minimization. We still have an additive form, but instead of having 1/n as weights over each of the datasets, we have weights for each of the datasets. And the idea is that the weights should put more emphasis on those points that are deemed vulnerable. And the core assumption is that, of course, our knowledge about the majority is greater, and we have more data points about the majority than about the minorities we would like to protect. So what's our basic proposal? So our basic proposal to emphasize this minority in our learning process is to estimate the density of the data and to generate and allocate the weights of the data points so that more sparse data or less dense data have higher weights. So to emphasize on them. And then once we have allocated those weights, to minimize the weighted loss to find a final model. So here you have an illustration of this process. So if you look here, you have the results of the density estimation with the poorly dense area that receive a high weight, or what we call a high epistemic uncertainty, because we lack basically knowledge for those points. And in redder or in darker shades, you have those data points that are very densely, those regions that are very densely populated and that we don't need to protect from bad learning. So to estimate those densities, we basically, in the work we present here, we used bars and windows around the data points. So clearly, classical density estimation procedures You can question, of course, when you do that, the kernel shape, the kernel width. So for the shape, we choose triangular, for instance, and the width is just the average distance between all the training points we have encountered. So, and here I would like to emphasize that we do not want exactly to estimate the density, which is a very hard problem, but just to rank the points from the less dense to the more dense points, which is arguably an easier problem to achieve. So it's also why the shape and the width matters a bit less, since we want to basically an ordinal information about the densities. So now how do we formulate the weights? For this, we use IDs that comes from the ordered weighted averaging approaches. So we first rank the points from the less dense to the most dense. And here you see on this picture how we assign the weights. So if we want to have a classical arithmetic average, we would choose, for example, the green line, which assigns equal widths or equal weights to each of the points. And if we want to emphasize the first point that we have ranked, so the less dense point in our case, then we pick a concave function, and in this case, a parametric concave function, and our choice was to have to train piecewise linear function and to play with piecewise linear function. So you see the idea is that the more the function we choose is close to the identity functions, the more we are closer to an arithmetic average, and the more we move towards the upper left, the more we put a greater weight on those points that are part of the assumed minority. So this is quite an efficient preprocessing because we have a sorting mechanism, and the eth data point receives the eth greatest weight. So everything so far is quite easy to achieve. And here are the results we have in our methods. This is a proof of concept. So you see that if we apply our strategy to our problem, we learn a model that remains quite good on the majority and becomes indeed quite better on the minority. So on the right, you have a drawing of the different curves we have chosen, and you have a drawing of the Pareto front of different models obtained with different concave functions. And here you see that we may, on the minority, so on the upper right populations, we can gain up to almost 10% of accuracy on this population without giving up too much on the total populations. This we drop by about 1 or 2%. So this is the results on our synthetic data sets. And we wanted, since we validated it as a proof of concept on such synthetic data sets, we wanted to see what happened on public data sets. So we ran our methods on about 30 different data sets, and we find kind of non-trivial trade-offs, but still very small ones on 3 data sets. So these data sets are listed here. It's the Istanbul Stock Exchange and 2 data sets from the UCI repository. And you see that here, well, the gain on the minority is very small, and the loss on the majority is slightly smaller, but still the results are not that great. One reason for that is that even with the arithmetic average, or with the classical empirical risk, the difference between accuracy on majority and minority is very small. So this is at least one of the reasons, but this was the case for almost 30 datasets. So this is quite disappointing because in the proof of concept, we showed that it was possible to give 1 point of total accuracy in exchange for an increase of 10 points on the minority. But on real datasets, such trade-offs are very rare. Okay, so this was quite disappointing. Of course, with out of different reasons for that. The reason is that, of course, it doesn't come, the link between model and reality cannot be questioned. So we are kind of in ID assumptions in this case. But in our case, at least for most data sets, the model learned via empirical risk minimization spreads error, at least for the models that we considered, that was logistic regression, in a somewhat spatially homogeneous way. So we have errors that are the same in every regions of the space, at least those regions we consider. Another explanation can be that the epistemic uncertainty, or the way we measure it, might fail to discriminate minorities on which we poorly perform. So this would be a reason. And giving more weight to less well-known areas often yields no gain, but because there was little to gain at the start, as I've said. Of course, it may also be due that we deal with a classification problem with a very simple classifiers. Also, this might depend on the data sets we consider, but we consider manual. Still, even if the results are a bit disappointing, we have great expectations for what's to come with this approach, because for one, we believe that our analysis of the shortcomings of the empirical risk is mostly correct. Let's show, for example, the proof of concept. There is also quite a normative and I would say even axiomatic appeal in representing the aggregated risk using tools from the social choice theory, because you have a lot of reasons that may say that this is a good idea, at least in social choice theory. So we would like to transfer those reasons to machine learning. And also that order-weighted averaging operators are very natural contenders because they allow to express various attitudes with respect to fairness, so which is what we see, fairness or equity, and they remain quasi-linear, which means that once you have done the sorting, then all the learning you have to do has the same complexity as what you do with empirical risk. So thank you, and if you have questions, you can send that to us or directly ask. Thank you.